Okay, let's begin. Questions on the homework?
Number 9.
12.4. 9.
It's just really bloody.
Huh?
It's just a bloody integral.
It's a bloody integral. What does that even mean? You guys are taking this battle analogy we've been using too seriously now. It's going too far. You have to attack this integral. Okay. What is it? What is the question?
This is a question where you have to bring it up.
To bring a gun. That's how we're going to solve it.
Okay.
That's exactly how it was described.
Yeah, the D and then
So they gave us the region D. This reminds me of something from differential equations. And they actually define the mass and center of mass?
I think so. Yeah, mass.
Okay. All right, so what does this region look like? Okay, so it's just from y's go from 0 to sine. So there's a sine curve going on. Where's the first time it hits 0? At L. Right, so that's 0 to L. And that's my x, and y is just this. So that's my region here. Okay, so we need to find the mass and center of mass of this guy. The density rho. So let's find the mass first. How do we do that? Well, it's a double integral over d of the density function. So x from 0 to L, y goes from 0 to sine pi x over L of y dy dx. This gives us y squared over 2. Plug in the sine, I get sine squared of pi x over L all over 2 dx. How do you integrate sine squared?
You substitute.
You what?
You substitute.
Right, do a trig identity, not a substitution. So this is 1/4 of 1 minus cosine 2 pi x over L. L. Okay, so what's this going to be? By the way, what's the period of this guy?
The period.
Yeah, what's the period of that trig function? All right, find the period of a sine function. Pre-calc, yeah. It's just 2L, so that's, yeah, so it would be 2 pi over the coefficient of x. So it's pi over L. It's actually 2L. So we don't go over a full period, so we can't ignore this guy really technically. So let's continue. Well, the period of this guy, would be L though, right? So we're integrating from 0 to L of this. I can essentially ignore the cosine if I choose. So I can ignore the cosine, so this is really just 1/4 of, from 0 to L of 1 with x. So then this is 1/4 x between 0 and L, which is L over That's the mass.
How do you do that? I mean, like, I don't understand how you know you can cancel the cosine. If it's going twice between L? Is that right?
No, as mentioned before, like just do this. Like if you have sine, this is what your sine function would look like, and your cosine function would look like this. Right? This is sine, this is cosine. If you're integrating here, the area here is actually equal to the area here. Right? So once you integrate over a whole period, you're going to get 0. Same thing for cosine. The area is here. Right? This would be a over 2. That would be a over 2. This would be minus a. Right? So if you're integrating over a full period, like from 0 to 2 pi of sine x dx, the answer is 0. Same thing for cosine. In fact, if you integrate over any period, that's a multiple, right? So if you go from a up to a plus 2k pi of sine x dx, or from a up to a plus 2k pi of cosine x dx, that will also give you 0. Also, we know that if your function looks like, if y is equal to a sine kx minus b plus c, or y equals a cosine kx minus b plus c, then the period of this function is 2 pi over k. Right? This is something you learned from pre-calc, right? So k is just the coefficient of this guy, a is the amplitude, b is the phase shift, c is the vertical shift. K is the guy who tells you how many times you go through a period, how many times you oscillate in 2 pi. So basically here, when I look at here, I can see that the period of this guy is going to be 2 pi divided by k, but k in this case is 2 pi over L. So this is just 2 pi over L. So I know the period is length L. So I'm integrating a cosine over its period, I can ignore it. So I ignored it. So whenever you're doing definite integrals for sines or cosines, this is always a consideration you can have in mind because it will greatly simplify your calculations. You can essentially ignore the indefinite integrals if you're integrating over a length that's a multiple of the period.
Professor, let's say you put some calculation on this on the test. Your final thoughts just cross. If we see that, we can just cross it out and say, or you want us to mark it somehow?
No, that would be fine for me. Because if I'm writing up solutions, I'd have done that, so whatever. Okay, so we know that the mass is L over 4. Let's start over here. Let's find the center of mass. I need to do that. I probably shouldn't have done that. I don't want to use this diagram. This is y equals sine pi x over L. So that was the mass. Let's find the center of mass. Center of mass. What's x bar? L over 2. No calculations necessary by symmetry. How do we find y bar? Right, notice by symmetry because our density depends on the y level, right? So our density changes in the horizontal fashion. It's stacking this way, right? There's nothing that's stacking this way. So my x would be dead center in the middle, right? So it's just a matter of where this point is along this line. L over 2 is going to be the balance point for the x because the weight only changes based on what the y is doing. The x has no say in that. So L over 2 is that guy. This guy is 1 over m times w rho d of y times rho x1. So our m was L over 4, so this is 4 over L times integral from 0 to L times integral from 0 to pi x sine pi x over L of y squared dy dx. So we're going to integrate this. We're going to get y cubed over 3 between 0 and sine pi x over L dx. Equals 4 over L times integral from 0 to L of sine cubed pi x over L over 3. Okay, how do I integrate this one?
Sine squared pi x sine pi x over L.
Right, so we split this up into sine squared, which is just going to be 1 minus cosine squared pi x over L times sine pi x over L over 3 dx. And then we do a substitution, right? So u is going to be what?
Cos pi x over
Okay. So my du would be?
negative. It's not sine x over pi x.
So my du is going to be a negative what?
Sine du. Yes, negative sine x.
Negative pi over L times sine pi x over L.
Yes.
Pi over L. So this is going to be L over pi. Over 3. Just keep that, bringing that guy with us. This is from x goes from 0 to L. So the L's cancel. I have minus 4 over pi. And here, I'd integrate this 4 over 3 pi. Integrate 1, I would get u. My u is actually cosine, so this is just cosine pi x over L. Minus, integrate this, I would get cosine cubed pi x over L over 3. So plug in L, I would get cosine of pi, which is cosine of pi. Again, plug in L here, I get cosine of pi, and which is negative 1, and I cube that, so I get another negative 1. So it's plus 1/3 minus, plug in 0, cosine 0. And here, again, I get 1, so this is minus 1/3. So that is minus 4 over 3 pi times minus 1 minus 1 minus 2. I have plus 1/3 plus 1/3, that's plus 2/3. That's minus 2 plus 2/3. Huh? Minus 4/3. So overall, multiply these, I get positive 16 over 9. So this means my center of mass is L over 2, comma, 16 over 9. Yeah.
How do we do a substitution 1/2 squared for the sine cube, or for the sine squared? We didn't want to pull out half and half. Or multiply that one.
Why would I multiply by 1?
Just not the half end.
My u I did a u substitution here. I didn't apply the half angle formula. So u was cosine. My du was minus pi over L sine pi x over L. So that went over here, that gave me that minus L over pi when I moved to the other side, and then the sign got rid of this, and so I ended up with just one mass. Other questions?
11.
What does 11 say? Okay, a lamina occupies a part of the disk s squared plus y squared less than or equal to 1 in the first quadrant. Find the center of mass as the density of any point is proportional to its distance from the x-axis. So rho of xy would be equal to what?
K
Hmm?
times 24 No, K times Y.
Ky? You
What did you say?
have to keep this PG-13. You're gonna have to like bleed this out. You're gonna see like a fuzziness right here. So we're just a quarter circle here because we are in the first quadrant. The y coordinate measures the distance from the x-axis. So being proportional to the distance from the x-axis means you're a constant times y. Okay, so yeah, this is just a circle of radius 1. So that's our lamina here. Okay, find center of mass. So in order to find the center of mass, we're going to need to find the mass first because that's in the formula for the center of mass. Mass is going to be double integral over d of rho xy dA. How do you set this up?
0 to pi over 2.
Okay, so we want to switch the polar coordinates. So we have 0 to pi over 2. R goes from 0 to 1. Ky would become
KR.
sine theta. dA becomes r dr d theta. So then I'm going to integrate this. This is going to be k r cubed over 3 times sine. So I'm going to plug in a 1 and a 0, so that's just going to be k over 3. Integral of sine is minus cosine. Which gives you k over 3. So that's the mass. X bar would be what?
3 times.
Hmm?
3. And then double integral is like 0 to pi over 2. And then 0 to 1. And then R.
Oh, so let me write it out because you're sort of simplifying first. You'd put 3 over k, but then you'd have the double integral of d of k y times x dA. The k's are going to cancel, which is why she only has a 3 there. So there's a 3 times 0 to pi over 2, 0 to 1. And x times y, this would be r squared cosine theta sine theta times r dr d theta. So that would be r cubed, so this is going to be r to the 4th over 4 times cosine theta sine theta. That just becomes 3/4 How do you integrate cosine theta times sine theta? Substitute what? Okay, tell me another way to integrate cosine theta times sine theta. You can write this as sine 2 theta over 2. Sure. Give me another way to integrate cosine theta times sine theta. So this suggestion was set u equals cosine, do a substitution. You could also use the half angle formula to write this as 1/2 sine 2 theta, double angle formula. You could also do u equals sine. There are a bunch of ways to integrate this. All answers would be equivalent. They'd only differ by a constant, so it's really a matter of taste. So I would probably, if I'm doing u sub, I'd say u equals sine, so that I don't have to worry about a negative sign factoring out. So this would just be sine squared theta over 2 in 0 and power to 2. Sine of power to 2 is? So this is just 1/2. That was my x bar. Y bar is going to be k over 3. The k is going to cancel just as before, and I'd have to double integrate. This is 0 to the power of 2, 0 to 1, and then I'm going to integrate y times y, so that's y squared, which is r squared sine squared theta, r d theta. This gives me r cubed over 3, which kills that. Sine squared theta, theta, from 0 to 1. So that's just the integral from 0 to the power over 2 of sine squared theta, theta.
Oh wait, no.
What?
It's gonna be r cubed, then r to the 4th.
R to the 4th
Yeah.
over
so
4.
3
How do I integrate this?
No, 3.
Come here.
Happens about 3.
The 3 wouldn't cancel, right? So how do we integrate this?
Oh, you do the
Half angle formula again, so this is 3 over 8 times 0 to the pi over 2, 1 minus cosine 2 theta, theta. This is 3 over 8 times theta minus 1/2 sine 2 theta between 0 and pi over 2. So this is going to give us 0 in either case, so then this just becomes 3 over 8 times pi over 2. Which means our center of mass is 3 over 8, comma 3 pi over 16. So, like I said, this was just doing double integrals. The main thing different in this section is the formulas that you have to know to set up. You know what m is, what x bar is, what y bar is. Other than that, it's just previous sections. Let's move on. So, last time I told you all the theory behind triple integrals. We never really did any examples of it. I'll do a couple of those. Move on to surface area. Talk about cylindrical coordinates. I don't think I'll get to spherical coordinates, but I'll try. Because the more time we have to go over series, the better. And I did tell you guys about volume, right? Volume is just a triple integral of 1. I did it up. So this is 12.5 continued. Let's do some examples. Why do I feel like I've done something? See tetrahedrons all the time. It's always a deja vu. Like I feel like I've done this before. It's because I have, like hundreds of times. Okay, so I said here what I wanted you to do was evaluate as a type 1. And then I want you to set up the type 2 and 3. To remind you, again, this is not something I'll ask normally, but I just want you to get the practice. Type 1 just means projection is in the XY plane. But I want you to practice setting up projections in other planes as well, because it does come in handy sometimes. It would be nice to draw a picture. So let's draw a picture. How do I draw this? It intersects each axis at 1. Plug in 2 variables equals 0 at a time to get what the point on one axis is. Each will be 1. And I'm bounded by the xy plane, the yz plane, and the xz plane. So we're all in the first quadrant, and this is a tetrahedron. Looks sort of like a pyramid, has 4 sides. The base is given by that triangle in the xy plane. So the type 1 would be looking at D in the xy plane. Which means my region of projection would look like this. 1, 1. Which means that could be described how? Y equals 1 minus x, and x goes between 0 and 1. Right, so y would go from 0 up to 1 minus x. How do I get that equation? Y equals 1 minus x. The fastest way to do it.
Plug in 0.
Plug in 0 for z, solve for y. Right? Don't bother, oh, y 2 minus y minus 2. You're wasting time. Just plug in 0 here. Okay, solve for y. Because we're in the xy plane, so that just means z equals 0. Okay, so now we're going to set up triple integral of e of 1 dv would be equal to, just to remind you how this works, the two guys out here have the double integral set up. Right? Which means they're described by what I just did with the region of projection. Right? The two outer integrals come from your region of projection. So I know right here, this is going to be x goes from 0 to 1, y goes from 0 to 1 minus x, always constants on the outside. Okay. What is the third integral?
0 to 1 minus x.
Right, so the third integral goes between surfaces. So that's what you have to remember, surfaces. Right, so I'm going to go from bottom to top. Right, so the bottom surface on this picture that I just drew, you see is the xy plane. That's just z equals 0. The top surface, the roof, would be this plane that cuts through the first octant. So it's just, I just take x plus y plus z equals 1, solve for z. I would get 1 minus x minus y.
Can you repeat it?
Come again?
Can you repeat that?
Oh, the inner integral goes between surfaces. So here I'm going to put the bottom surface and the top surface here.
How did you get the top surface?
Well, again, this is sort of what you want to do. Just imagine you're a little guy trapped inside this pyramid. If you look up, what's the roof? It's going to be this slanted plane that's cutting across over you. the plane has equation x plus y plus z equals 1. Since I'm projecting in the xy plane, I need to write that as a function of x and y. Therefore, I just solve for z. Right? So the roof would be z equals 1 minus x minus y. The floor I'm standing on would be z equals 0. So this is 1, and I do dz, dy, dx. That would be a type 1 setup. Let's evaluate that. What does that become? Let's see. Between 0 and 1 minus x minus y, dy dx. So that's just from 0 to 1, 0 to 1 minus x of 1 minus x minus y dy. Integral of this, y minus xy, y squared over 2, between 0 and 1 minus x. Plug this in for the y because I just integrated with respect to y, so this is 1 minus x times 1 minus x minus 1 minus x squared over 2. And if I plug in 0, everyone's 0, so that's just dx. This out here is 1 minus x. So this is 1 minus 2x plus x squared. Let's finish that up over here. Equals, so we integrate that with respect to x. So the integral of 1 is x. The integral of 2x is x squared. The integral of x squared is x cubed over 3. What's the integral of 1 minus x squared over 2?
Plus 1 minus x, 3 to 6.
Right? You just do a substitution here. The du would be -1, so that changes the negative sign to a plus, and so you get u squared over 2. The integral of that is u cubed over 6, hence you have this with a plus sign. Plug in 1, I would get 1 minus 1 plus a third plus 0 minus, if I plug in 0, the 0 minus 0 plus 0 plus 1/6. So I basically end up with a third minus a sixth, which is a sixth. Yeah.
You could have expanded on that, right?
I could have expanded that. I could have also treated 1 minus x squared over 2. I could have written as 1 minus 2x plus x squared all over 2. I'd end up with a half minus x plus a half x squared. But I don't particularly like fractions if I don't have to deal with them, so I didn't do that. I just realized that the derivative of this is a constant, so I can pretty much think of this as a variable. Just think of it as u, and then the derivative would be divided outside here. Oh, which reminds me, I need to mention that, because someone told me about something that they saw on YouTube from a very nefarious site. Apparently someone told them that if you have the integral of, what was the example of it? Like the integral of something like e to the x squared, right? Like the integral of that was 1 over 2x e to the x squared. The reasoning was what? Well, if you let u as this, then your du is 2x, and then you just divide by it on the other side. Yeah, that's totally wrong. Right? So that sort of trick you can use only when your derivative is a constant. So I want to make sure I mention that. So you can use that trick when your derivative is a constant. So something like this, if you let this be u, the derivative is just k, and you can just divide by the k, right? Right? So you can do that when it's a constant. You can't do it otherwise, just so you know. Just wanted to mention that. Right. You don't just integrate by dividing by the derivative. It doesn't work if the derivative is a function. That's not how substitution works. This has no antiderivative property.
Like none at all, or nothing that we can solve for?
Nothing in terms of elementary functions. We basically invented a function to use as the antiderivative. So there's no function we can think of that is a combination of polynomials, exponentials, trig functions, or any functions we've seen before, where if we take its derivative, we get e to the x squared. So we pretty much invented a function. Just like we invented radical of -1, we just call it I. We don't really know what it is. It's something we've never seen before. Just put something there. So this is one of those guys. Okay, the other two setups. So we have this region here. Set it up in another way. What if I want my region of projection to be in this plane? How would that setup look? Right? So now gravity got confused, and I'm now standing on one of the walls. How would that integral setup look? What's the first thing I'm going to do?
Double integral portion.
Find the double integral portion of it, which involves doing what?
Projecting on the.
Figuring out what the projection is doing. So I'm going to look at the projection, and now the projection is in the xz plane. So this is z versus x. And it would look like there's a 1 on the z, 1 on the x, so it's that. And so how would I describe that?
C is 1 minus x.
Z goes from 0 to 1 minus x, x goes from 0 to 1. So then my integral setup would be 0 to 1, 0 to 1 minus x. There's an integral here, there's a 1 here. On the outside, I'm going to have dy, dz, dx. What goes on the inner?
0 to 1 minus x minus b.
Right. So again, now I'm standing on the floor, but that is the equation y equals 0. Right? Now once I decide to put my projection region in x and z, it means all my other functions must be y equals a function of x and z. Right? So I must describe all my surfaces in terms of y equals something. Right? Which means that this surface here, when I look up to the roof, again I see the slanted plane. How am I going to represent that?
Y is equal to 0.
Y is equal, no, the slanted plane.
Y is equal to 1 minus x.
1 minus x minus z. Right? So that's what I would put here. 1 minus x minus z. And that integral will also give you 1/6. And again, I could have decided, if the inclination struck me, to project onto this wall, where now I'm standing on this wall. In which case, when you're setting up a triple integral, the first thing you're going to look at is your region of projection. So I'm going to worry about what the shaded portion is doing. Now the shaded portion is in the yz plane, which again is going to look like this. I can set this up as z goes from 0 up to 1 minus y. And my y goes between 0 and 1. So here I would have 0, 1, 0 to 1 minus y. There's a third integral, which is going to be dx, dz, dy. What is the third integral going to look like? Well, I'm standing on the floor. The floor is now x equals 0. The roof is now x equals 1 minus y minus z.
1 minus z. Could you do how we have to?
Oh, yeah, I could have let z go between 0 and 1. I could have done 0 to 1 and choose y to go between 0 and 1 minus z. This would be 0 to 1 minus y minus z. This would be 1 dx, dy, dz.
So there are 6 ways to do anything.
There are 6 ways to do it, yes. You choose whichever one is convenient. As you'll see, in this case, every way was very similar. You don't get much difference in terms of integrals, but there are cases where it actually matters greatly the way you set it up. Sometimes you have to split things into 2 integrals. But if there's ever a case where you need to project on something other than the xy plane, you need to know how to do it. It all comes from choosing where am I going to project, figure out what that shaded region is doing, right? Describe it in terms of constants and functions. That gives you your 2 outer integrals. Then you describe the function as the variable that's missing. You have to write everyone where he's on the left side. X equals blah, x equals blah, right? And that's going to define your third integral. Right? You'll soon see cases where this actually matters. So basically what I'm saying for now and for the rest of your math courses forever, from now on, don't get fixed to one position. Don't always think you have to stand on the xy plane. You can stand anywhere, right? Gravity is not a prison for us anymore. Other example, evaluate the triple integral over e, y squared plus z squared, dv. Right? So everything can be permuted. You can think of the variables in any order you choose, where e is the solid bounded by copy that down. Okay, what kind of surface is this? X equals 1. It's a plane. What kind of surface is that? Paraboloid. Good, like the reaction time. So you think of it as x equals y squared plus z squared. Now let's see, can we draw a picture here? How does it look? Opens towards where? Positive x, so it opens this way. And then x equals 1 looks like what? Chopping it through here, the plane is going to be parallel to the YZ plane. So there's going to be a plane cutting through 1 that's going to chop this paraboloid. So we're seeing sort of this. So this is our object. This is sort of. Okay, set up the triple integral. How do you set up the triple integral?
You do projection on the YZ plane.
You project onto the YZ plane. Seems like a nice thing to direct. So you shine a light this way so that the light shines on the YZ plane. You project there, you'd end up with that's the region projection D. Right? So basically we're going to set up this triple integral where the two outer integrals are going to describe this region D, and then the third integral is going to describe surfaces which are functions of what?
Functions of x.
No. X is the dependent variable here, so it must be functions of what?
Oh.
Y and Z. Right? So just by choosing your projection, you already sort of know what your triple integral has to look like. The inner integral has to have variables y and z. The outer integral is going to describe the region of projection, which is in the yz plane. Right? So we are going to do let's go plus z squared dv. Okay. So let's worry about d. Right? So we draw the 3D picture just to get the 2D image of the region of projection, right? So then we draw a second picture. This is our region D. Now, what is the equation of the region D? How do you get that? Right. Notice where this projection comes from. It came from the outline of this curve here, right? Well, what is that curve? This curve represents the intersection of x equals 1 with x equals y squared plus z squared. How do you find intersection? You substitute one into the other. So I pretty much plug x equals 1 into that equation. And so the equation for this would be y squared plus z squared equals 1. So it's basically a circle radius 1 in the yz plane. How do I describe that region? I could do it in polar coordinates. So I can choose my r and theta. What's my r doing? What's my theta doing? 0 to 2 pi. And so my dv, I'm thinking of it here as dx times dA, right? Where my dA would now become what? R dr d theta. Now we can set up the triple integral. So here I'm going to have r times dx dr d theta. What's on my two outer integrals? 0 to 2 pi, 0 to 1, coming from here, right? From my region of projection. That matches with this. R goes from 0 to 1, and theta goes from 0 to 2 pi. What has to happen on the third integral?
Y squared plus x squared on the bottom.
R squared.
Y squared plus z squared.
Right, so again, this is describing a solid figure, right? And you're a man trapped in this solid figure, right? But you're standing over there. If you look up, what do you see? What's the roof? The plane. X equals 1 will be the roof. So 1 goes on top, because that's the roof. What is he standing on? He's standing on the paraboloid, right? That would be the bottom. That would be the floor for him. Now the paraboloid is x equals y squared plus z squared. However, my y and z, I just switched to polar coordinates. So if the floor is x squared plus y squared, x squared plus y squared plus z squared, what does that become? R squared. Because now I'm thinking of this equals r sine theta and z equals r cosine theta, right? I'm pretty much switching the x for the z for the x-axis, right? So then my y squared plus z squared just becomes r squared, which is down here, So I have x equals r squared up to x equals 1. Now I have to worry about changing that y squared plus z squared, which we just told you what that was. That's also r squared. Right? So this is the setup for the triple integral here. Oh, a bit too late for this, but it's a spoiler alert. Basically what I just taught you was cylindrical coordinates, which is actually 12.6. Right? So in 12.6, I'm going to teach you how to set up things in cylindrical coordinates, which I just taught you how to set up things in. Right? So basically, cylindrical coordinates is like treating dV as this guy, where the dA is just polar coordinates. That's all you were sort of thinking of. So, but we'll go over that in detail later, but we've already done it here. Without polar coordinates, it would have looked a lot uglier. We'd have something like -1 up to 1, and then minus the radical of, I'd have to solve for one of these guys. So I'd have like minus the radical of x minus y squared up to a positive radical of x minus y squared, and this would be like dz dy. It would look nasty. Okay. But that's cylindrical coordinates. Let's evaluate. So spoiler alert, this is section 12.6. Which I just taught you the fundamentals of that. I probably don't have to teach it now. Okay. We'll go over it. So we have 0 to 2 pi, 0 to 1, r squared up to 1 of r cubed dx dr d theta. So turns out the d theta is going to give us 2 pi. Remind me to tell you something about that, what I just did just now. Okay, so now what? Integrate this with respect to x, what do I get? R cubed times x, where x goes between r squared and 1. Because I have to explain what I did. I'm going to explain it in detail. I applied a principle that you can apply in general. I want to mention. Here. So plug in 1, I get r cubed, minus I plug in r squared, get r to the 5th. 0 to 1, 2 pi dr. Gives me r to the 4th over 4 minus r to the 6th over 6. One-fourth minus 1/6. What's that? 1/12?
Yeah.
So it's pi over 6. Okay, let's go back to star. Remember, this was mentioned in the syllabus. If I have a function like f of x times g of x dx, and then you sort of do this, you integrate the f, and then you multiply by the integral of the g, that's a blasphemy. Okay, so don't do anything like that, right? So I've seen people do that. They see things like the integral of x times sine x dx, and they think that's equal to x squared over 2 times minus cosine x plus c. That is wrong. That's a blasphemy. You get 0. Okay. In triple integrals, though, there's something that might seem to you like a blasphemy, but it's actually not, which is what I applied over there. I just want to mention it to you now so that it'll make your life easier later on. However, let's say you have a double integral, and it's something like dx dy.
You can do dy instead of dx. Is that right?
So let's say I can actually, the function I'm integrating looks like this. It is a function of x times a function of y. Right? Notice that this function purely of x this is a function purely of y. Right? They can't commingle, right? You can't have x's and y's mixed up in here and x's and y's mixed up in there. If one guy's is a function of x, the other guy's a function of y, then you can literally split the integrals. You can literally think of this as f of x dx times g of y dy. And why can I think of it that way? Yeah?
Because if you do one side, it will give you constant.
Right. So when you have a double integral, remember when you're doing dx, right? All y's are constants to you, right? So if I'm focusing on the dx, the inner integral, my g of y is effectively a constant. There's a rule of integration that says I can factor constants out, right? So if this is purely a function of y, I can literally just factor it out. I can factor out one of the integrals, because with respect to x, this guy's a constant with respect to x, right? This guy here is a constant with respect to y. The f. So, example, if I see something like 0 to 1, 1 up to 3, or something like x, y squared, dx, dy, I can literally just think of this as y squared dy from 0 to 1 times 1 up to 3 of x dx. Notice that there are only y's over here, there are only x's over here. Okay? So that's the important part. Only y's. Only x's. So applying that principle to something like this. Let's say I have a double integral, I have 0 to 2 pi, I have 0 to 1, or something like r dr d theta. Right? I can sort of think of this as, see, there's just r's here, right? Which means my dr integral, I can just think of it on its own. There are no thetas, so as far as theta is concerned, it's a constant. I can literally like factor this guy out. I can think of this as 0 to 2 pi of 1 d theta times 0 to 1 of r dr. Right? Integral of 1 is just theta, right? So that would just be theta between 0 and 2 pi, which is just 2 pi. So it's not uncommon for me seeing this, I would literally just write 2 pi times 0 to 1 of r dr. Right? I might just make that step. It'll skip all this work. Right? Because there was no thetas here. I could literally just like factor the theta part out. Okay? So there are times when it's not a big deal here, but it will be. There are times when your function of theta is like complicated, and you'd have to keep bringing that with you, you know, while you're working on all the other variables. That's opportunity for mistakes, because a lot of people just don't copy things down correctly for whatever reason, right? They're gonna miss a square or something, right? So you can literally just get the theta out, deal with them separately, so you don't have to bring him with you the whole time, right? So things like that. So if I'm doing something like 0 to 2 pi 0 to 1. Let's say I have r times cosine theta sine theta, or times sine squared theta. Or even worse, let me do something worse. Something like r times the radical of 1 plus 4r squared. Okay? Now when you're doing that, you're going to have to be doing a substitution on the inside, right? So you have 0 to 2 pi, say 0 to 1, whatever. Okay? So to deal with this part, the dr, you're going to have to be doing a substitution, right? Now while you're doing the substitution, you just have to keep copying this guy down, right? You're in a test, 5 minutes left. Oh my God, you start freaking out. All of a sudden, magically, the square disappears. Oh, I didn't see that stupid mistake. I forgot to copy it down. You know? So it's like, you would have to be working on this, and this guy's just hanging out because you're integrating with respect to r. You don't do anything to this guy. So he's just someone you keep copying down over and over. But then eventually, things start falling off. A minus sign disappears. A square disappears. Right? And all sorts of crap. Your answer becomes totally different. And I get all confused. I'm not grading this, just 0. So, and then, oh, chose me. Yeah, so this sort of, knowing this kind of thing will sort of save you from that. You sort of know that I can just deal with this guy, evaluate it, put him as a constant on the outside. It's much easier to evaluate it as a constant. Right? So I know that the integral of this would be what? Just tell me. Sine cubed over 3, right? Now if I plug in 0 and 2 pi, what's going to happen? That's just a 0. I can literally factor out a 0. What's the answer? Right? Now imagine if you didn't see that. You're going to be like, okay, u equals 1 plus 4r squared. You're going to keep copying this guy down. At the end of the day, he's going to give you a 0, and none of that work is going to matter anyway. Right? So you're there like 15 lines down. Oh my God, I forgot the square. You have to go back up, double angle 4, use substitution on that. For nothing. Right? So little tricks like that, they sort of save you a lot of work. Other tricks like the one I showed you about knowing if you're integrating a sine or a cosine over the length of a period, you know it's 0. You don't do it. You'll appreciate things like this when you get to your engineering classes especially. You'll see like these huge, insane integrals, like, oh my God, this is so unfair. But really, it becomes nothing if you know what to look for, how to simplify. You're like, I can ignore that part, I can ignore this part. This guy's just going to be a constant I factor out. The integral is a stupid little integral. But it started like a really huge, long one. Right? So no tricks like that I just used. You can do those in general. The important part is the variables have to be isolated. If I had a theta in here, it doesn't work anymore, right? Because now that is not a constant with respect to this guy. But as long as things can be isolated, I have a part of this that is only r's, I have a part that's only thetas. I can literally just deal with them separately and multiply the answers together. Okay. Just wanted to mention that. $13.6. Yeah, so something like what I did before, like just seeing this and putting a 2 pi out the front, I'm going to do that all the time. So I just wanted you to know why I can do that and what's going on. So there's a lot in this section, but for Calc 3 we don't need most of it. The main part I'm going to take from this is the surface area formula. There are actually a couple of formulas for surface area, but there's only one that I want to focus on. It turns out that if you want the area of a surface z of x, z equals f of xy over given y. Turns out, make the region of projection D and integrate the normal vector to the surface, and that actually gives you surface area. So what I'm saying is, here I have a surface floating around. This is z equals f of xy. My projection is in here. That's D. If I do this integral, it actually gives me the surface area of this guy. The area of this surface, the part of it that's over that projection, is equal to the double integral of the magnitude of the normal vector. Okay. More on this in 392. When you do 392 vector calculus, they're going to talk about this, why it's true and blah, blah, blah. In Calc 3, we don't care. Right? I'm just going to give you the formula. So your professor will probably derive that for you. Why is the surface area that? But for now, just know that's what the surface area is. It's one of the ways. There are multiple ways to find normal vector, but so far we do know one way to find a normal vector. What was that? Huh? The tangent plane isn't a normal vector. The normal vector to the tangent plane would be how we do it. How do we find the normal vector to the tangent plane? What? Give me a nicer, compact. There's a vector. The gradient vector. Okay, so now, if we know that z is equal to f of xy, how do I find the gradient vector to that surface? Well, I bring everything to one side, remember? I think of that as my function f of x, y, z. And this means that my normal vector is just the gradient of f, which is just going to be fx, fy, minus 1. Which means that the magnitude of my normal vector is the radical, this squared, plus that squared, plus 1. This means the area That's it. So in calculus 3, if I ask you for surface area, this is what you're going to use. Yes, I will test you on it. It always comes on a final. The other ways to find surface area pretty much never comes on a final. But if it happens to be on yours, I'll tell you about that later. It'll take me like 5 minutes to explain that way as well.
Well, you're going to know what our final looks like before.
Yeah, I should, yeah. Usually when the department writes the final, they submit it to all the professors teaching it to see if there are any mistakes or typos or, oh, hey, this poem's unfair or whatever. It goes through a few revisions before. I don't know. Depends on who's writing. 2 weeks, 3 weeks maybe?
Could you give us a copy?
No. Anyway, so that's what we're going to use though. That's the guy that shows up in Calc 3 all the time. Let's actually do, of course there's a caveat here, but it always applies for us. So f of x, f of y are continuous. this works if they're continuous, which in our case they always will be, so let's just move on. Here's an example. Find the area of the part of the plane two x plus 5y plus c is 10 lies inside the cylinder x squared plus y squared plus 9. That's one example. What does this guy look like?
The x is 5, y is 2.
Right. So I'm going to graph the plane first, plug in z and y equals 0, x equals 5. So this is going to be at 5. Plug in x and z equals 0, y equals 2. Plug in z equals x and y equals 0, z equals 10. So my plane sort of looks like this. What's the other guy? What does this look like? It's a cylinder. How does it?
Radius 3.
What axis is it running along?
Z.
It's running along the z-axis, and its radius is what? 3. So it's going to cut through here, see 3, and cut through here. So basically I have a plane slicing through this guy. It's going to look like, I'm just going to redraw this in better perspective. Basically what it's going to look like, it's going to look like an ellipse slicing through this thing. This is going to cut through at 5. This is at 3. The other part of the plane will cut through at 2. And then there's a part that cuts through at 10. But basically there's a plane slicing through this cylinder. Right? That's what you want to see. It's going to look elliptical because it's slanted. Right? So I want to find the area of this surface. What's the area of that slanted ellipse? How do we set it up? Find the partials of what?
The plane. The FX, YZ.
Equation of the plane. So this guy I'm going to write as z equals f of xy, which in this case would be 10 minus 2x minus 5y, which means my normal vector. So I'm going to find the partials. Fx equals minus 2, Fy equals minus 5. This implies the radical of fx squared plus fy squared plus 1 is just the radical of 4 plus 25 plus 1, which is just the radical 30. Okay, so that's the number I'm integrating. What's the function now? How do I set up the integral? I need to set up the double integral over the region D. Where's my region D?
Down. XY plane.
Right, so I project the light down. In the xy plane, it's going to be a circle, right? Because I'm on the edges of this cylinder. What's going to be the equation for that? X squared plus y squared equals 9. That's what they told me here. So my A is going to be the double integral over D of radical 30 dA. Okay? Who can tell me the answer in one line? Huh?
You do your 2 pi trick.
2 pi trick. It's even easier.
4 pi radical 3.
6, 5.
6 pi radical 30, how do you get that?
2 pi out. And then you have 0 to 3 the bar. You just multiply 3 by 3.
You're thinking too hard. It's not going to be 6.
6 pi.
9 pi radical 30. Why? Because this is just radical 30 times the double integral of D, 1 dA. What's 1 dA? The area of D. What's the area of D? It's a circle, pi r squared. Or, we could have done 0 to 2 pi, 0 to 3 of radical 30, r d theta. So you're going to get radical 30, r squared over 2 between 0 and 3, 0 and 2 pi, d theta. You plug in the 3. So we're going to get 9 over 2 radical 30 times integral from 0 to 2 pi of d theta. That's going to give me theta, plug in the blah, blah, blah. We're going to get 9 over 2 radical 30 times 2 pi. The 2's are going to cancel. 9 pi radical 30. Okay. So we can start this off. 5 minutes left. Oh my god, what's the integral of r? Okay. Or you could have just done that. Oh my god, how do I integrate all? There's only 5 minutes left.
So the radical 30, that kind of acts as like the average value of the slope?
Kind of, yeah. Yeah, but you can just think of that area. It's just going to be a constant times the area of the circle. Because we're just sort of the area of the circle, but it's stretched. Right? You can see I just take the same circle and I stretch it. So it's just going to be a constant times the area of the circle. It's not always that nice, but I chose this example to highlight something. Sometimes you got to know the tricks. Especially for those of you who are prone to like copying things down incorrectly or making silly mistakes, it's good to be able to double check your answer with something shorter, right? So if you didn't see this and you see that and you're thinking, you're one of those people who always drops their signs, or oh, maybe I left the sign off, maybe I did this. Is there another way I can verify this answer? Yes, there is. There's always something else. Or if you did it the shortcut way and then you run through your test and you have time left over, you might as well just try the other way just to make sure you're right. Another example. Area of the art of to the right of the xy plane. So our next test is on chapter 12. Which we have 2 more sections after this to go over. So it's on chapter 12 and 13.6. So let's see. Tomorrow, I don't think I'll do MATLAB tomorrow, because you'll probably need to know about these other things before I can give you the next MATLAB. So tomorrow I should be able to finish 12.6. On Tuesday, I might finish 12.7. It might take a while to wrap your heads around it as well. Tomorrow we'll do 12.6. So test 3, it's going to be November 24th or December 1st. This one's more likely.
Is that Thursday? No.
That's a
Tuesday.
Tuesday. These are both. Oh, wait. So the next one, if I don't give it on the Tuesday, I give it on the Thursday, which is actually the 20th. Well, that's thanks. We'll have that off. That's why it's December 1st. Right? Because when is Thanksgiving break? It starts on the 25th, right?
Thursday and Friday.
But Tuesday we're here.
Yeah.
Right. So it'll either be right before Thanksgiving or right after Thanksgiving. Right before Thanksgiving seems more likely.
Everyone's
No grading for you.
Huh?
You don't get graded. Thanks.
I mean, it'll be nice to be the 24th. Of course it would be. You guys ever seen those Drake memes when he's like partying? It's like when you're at the club getting down, and then in the next page he's like,
Yes.
but you remember that, you remember something else. You remember that you left your phone at home with Babe. Right? So then you're going to be Thanksgiving eating turkey, everything's happy. You're going to remember your top 3 test. You know, you don't want that. You just want to be happy. So it'll be nice to be the 24th. While you're eating turkey, you're crying over triple integrals. I'm so thankful. Okay. All right, quickly, let's do this. What do we do? What do we do? I'm confused. We draw it. That's always a nice start to figure out what the heck is going on. What is this? What does this look like?
Parabola along the y-axis.
Where is it opening up?
The positive direction.
It's opening like that. Okay? This is the xy plane, this is on the right. And my y is less than or equal to 1, which means I'm going to have y equals 1. I care about everything less than that. So this is my object. It's hollow. Right? I just want the area of the skin. Okay, how do I do that? What's the first thing I need? We could use the normal, so let's think of this surface. How do we want to represent it? Well, they already represented it for us. They said y equals x squared plus z squared. Think of that as my f, right? F of xz. So what am I going to need from that? The gradient, which is going to come from the partial, so I can just do fx and xz.
2x and 2z.
2x to z, which means that if I take the radical fx squared plus xz squared plus 1. That would give me the radical of 4x squared plus 4z squared plus 1. Okay, so that's going to be the guy I'm going to be integrating. Over what region? Okay, so once I think of my function as xz, it means my region of projection is in the xz plane. So I'm going to shine the light in this direction. It's going to be a circle. How do I know the equation of that circle? What's the equation of that circle? X squared plus z squared equals 1 because it's the intersection of y equals x squared plus z squared with y equals 1. So I just plug in y equals 1. So that's my circle. So that's my region of projection. How do I describe it? How can I describe this region of projection?
R squared is equal to 1, R is equal
Right, so it's r squared equals to 1, because my x squared plus z squared, I'm thinking of as r squared, so that's polar. So r goes between 0 and 1. Theta goes between 0 and 2 pi. It's a full circle. So now my area would be equal to the double integral over d of the radical of 4x squared plus 4z squared plus 1 dA. Switching to polar coordinates, I get 0 to 2 pi, 0 to 1. What is this? 4r squared plus 1. RD theta. So that integral will give me the area. And here, there are only r's. My d theta is just going to give me a 2 pi on the outside. So how do I integrate this? U substitution, u equals what? 4r squared plus 1. My du is going to be 8r, which I'm going to put a 1/8 on the outside. So there's a 1/8. So this I'm going to think of as u to the 1/2. Add 1 to the power, you get 3/2. 4r squared plus 1 to the 3/2. Divide by the new power, you get 2/3. 2, 0, 1. Which is going to be equal to 2 times 2 is 4, goes into this 2 times, that's going to give me pi over 6 times. If I plug in 1 here, I would get 5 to the 3 over 2. Minus, if I plug in 0, I just get 1. So that's going to be the area. Here's a challenge for you. What if I ask for the area of the part of y equals x squared plus z squared in the first octant between the planes y equals 1 and y equals 3. What would the setup for that look like?
You need to go from 0 to pi over 2 and 1 to 3 of that function.
Would it be 1 to 3?
1 to radical 3.
1 to radical 3. Right, because this guy would look like, you would draw that. There's the plane y equals 1 and the plane y equals 3. So you're just getting this part of the surface here. that's in the first octant between the planes y equals 3 and y equals 1. The region of projection would just be a part of an annulus between 1 and radical 3. So that would be. Right, so I can describe tons of different regions. You need to figure out what they look like, what your region of projection is, and so on and so forth. And that's time. So homework for 12.5 and 13.6 due tomorrow.
Wait, there is no.
What?
13.6.
I didn't put any homework.
I know you did.
I think I did.
Yeah, you did. 71 to 41.
Yeah.
33.
Okay, that's it. I'll see you tomorrow.